Hey everyone, welcome to The Explainer. So, if you're a focused learner who has ever sat there, stared at your PC, and wondered what is actually happening inside that mysterious little black box, well, you're in the perfect place. Today, we're taking a highly structured, totally visual journey to demystify the central processing unit. We're going to break down how this incredible piece of silicone actually works, how to choose the right one, and even how to physically install it without, ruining everything. Let's get started. Okay, let's dive into this. Here is our roadmap for today's zoom in, zoom out narrative. First, we'll meet the computer's brain. Then we'll zoom into rings and system calls, pull back to compare clock speed versus cores, tackle throttling and thermal limits, and finally, walk through installing your processor. Section 1. Meet the computer's brain. Think of the CPU as the absolute shazam-a-lack-a-blam of your computer. This architecture really traces its roots back to the late 60s with chips like the Intel 4004, and it operates on what's known as the von Neumann architecture. Every single click, every game, every keystroke goes through this one tiny piece of silicon, and to understand how it works, we just need to look at its basic anatomy. Right at the core, you have the ALU, or Arithmetic Logic Unit. The ALU is basically a relentless math wizard. It handles all the addition, subtraction, and logical comparisons. Working right alongside it is the control unit, which acts kind of like a traffic cop directing data. And then you have memory registers. These are microscopic, lightning-fast storage buckets built right there on the silicon itself, holding the immediate data the ALU needs to do its job. And this brilliantly illustrates the actual heartbeat of your computer, the fetch-execute cycle. It's a simple four-step dance. First, the CPU uses an instruction pointer to fetch the next piece of code from your RAM. Second, the control unit decodes what that instruction actually means. Third, the ALU executes the math. And finally, the result is stored right back into memory. This cycle doesn't just happen once or twice, by the way. It is happening literally billions of times every single second. Section 2, Rings and System Calls. Let's zoom way down to the microscopic level here, because here's a secret. CPUs are fundamentally pretty naive. They'll just blindly execute whatever instruction is next in line. So to protect your computer from a poorly written app or worse, malicious software, the processor uses a highly secured two-ring vault system. In the outer ring, which is user mode, your everyday apps like web browsers live with strictly restricted access. But deep inside the vault is kernel mode. That holds the master keys to all your memory and hardware, and it's exactly where the core of your operating system lives safely isolated. So, you might be wondering, if user mode is totally locked down, how does an app actually save a file or connect to the internet? Well, it uses a syscall. When an application needs to do something real in the system, it sends a specific software interrupt code. For example, if you're using Linux, that's often int 0x80. This code acts as a highly controlled bridge, safely handing control over to the OS in kernel mode. The operating system basically says, okay, let me check if this request is safe, does the dirty work, and then securely returns the result to the app. No crashing the whole system. Section 3. Clock speed versus cores. Now, what's really interesting about this concept is how we can reframe it. If you're shopping for a laptop in 2026, you're definitely going to be staring at a spec sheet, facing the ultimate buyer's dilemma: higher gigahertz or more cores. We can demystify this with a really simple construction analogy. Think of your CPU like a construction crew. The cores are the actual number of workers you have on the site. The clock speed, which is measured in gigahertz, is simply how fast each individual worker can clear out their daily to-do list. If you have a task that can only be done by one person at a time, like loading up a web page or running the core logic of a video game, you want high single-threaded performance. That means a high clock speed. But if you're dealing with a massive task that can easily be split up, like exporting a 4K video or 3D rendering, you want multi-threaded performance. You want a high core count. The cool thing is, today's modern processors use hybrid designs to give you the best of both worlds. They dynamically balance high-power performance cores with battery-saving efficiency cores. You'll see this with Intel's P-cores and E-cores, or AMD's Zen 5 and their compact Zen 5C architecture. Let's make this totally practical with a quick buyer's matrix. Office workers and students, honestly, just focus on efficiency. A modern 6 to 8 core processor like a Core 5 or a Ryzen 5 is completely plenty. Gamers, you absolutely do not need a million cores. You need 6 to 8 really fast cores paired up with a great dedicated graphics card. But if you're a video editor or a software developer compiling massive amounts of code, yeah, that's exactly when you want to pay a premium for 10 or more cores to just chew through those heavy multi-threaded workloads. But wait, Raw gigahertz numbers really aren't the whole story. You also have to look at IPC, or instructions per cycle. That's basically how much actual work gets done per clock tick. A modern 3 gigahertz chip will absolutely destroy an older 4 gigahertz chip just because its internal architecture is way more efficient per tick. And we literally cannot forget about cache. Cache is lightning-fast memory built right into the processor. Having generous L1, L2, and shared L3 cache prevents your ultra-fast CPU from just sitting around bottlenecking, waiting on your much slower system RAM to feed it data. Section 4. Throttling and Thermal Limits. All right, it's time to introduce the main villain of our story, heat. This is exactly why those incredible boost speeds advertised on laptop boxes often cannot be sustained all day. If your laptop suddenly feels like it's crawling, your apps are lagging, and the chassis is burning hot, we're talking pushing near 100 degrees Celsius, you're experiencing thermal throttling. So the crucial point is, this is not a glitch. Thermal throttling is actually a built-in survival mechanism. It's the processor actively, deliberately slowing itself down to protect from literal physical silicon meltdown. The technical term for this self-preservation is dynamic voltage and frequency scaling, or DVFS. When the thermal sensors start screaming that it's getting way too hot, the CPU drops its voltage and lowers its clock speed, shifting down to lower P states just to survive the heat or stretch out your battery life. If you want to fix this, you've got some rapid-fire practical options. Clean the dust out of your fans, adjust your OS power plans, or look into tweaking BIOS limits and undervolting, which actively reduces power consumption without sacrificing any of your performance. Section 5. Installing your processor. Okay, we've talked theory, we've talked specs, but now it is surgery time. If you're building a PC, handling this incredibly powerful but surprisingly fragile silicon brain requires high stakes and very steady hands. First, you've got to know what you're dealing with. Older AMD AM4 chips use a pin grid array, or PGA. That means hundreds of fragile little pins are sticking out of the bottom of the CPU itself. Modern Intel and newer AMD AM5 chips use a land grid array, or LGA. The bottom of the CPU just has flat pads, and the microscopic fragile pins are actually inside the motherboard socket. In either case, listen to me. One bent pin and it is game over. Do not take the CPU out of its protective plastic tray until the absolute last second. Let's see how this builds out in practice, because it's a high-tension process. Step 1. Push down and out on the motherboard's metal retention lever to pop the socket open. Step 2. Find the tiny golden triangle on the corner of the CPU and align it perfectly with the matching triangle on the socket. Step 3. Gently lower the CPU straight down into the socket. Do not push it, do not click it, just let gravity do the work. Step 4. Slowly press the retention lever back down. You're going to feel some tension, but when it finally locks, wow, you'll feel the incredible relief of a safely installed chip ready for thermal paste and a cooler. And that brings us to the end of our journey. In 2026, massive AI data centers are just eating up high-end CPU stock and forcing this constant architectural evolution. We demand more speed, we want more cores, and we need more efficiency, all while battling the literal physics of heat. It really makes you marvel at the microscopic complexity sitting right there under your keyboard. So, as AI demand continues to skyrocket and push prices up, how will these tiny, heat-generating squares of silicon continue to evolve to run our modern world? Something to think about. Thanks so much for learning with me today, and keep exploring.